So thanks for attending today's WISCAN Compound Events webinar. And we're changing the format a little bit this time, just kind of to experiment, see how it goes. So we'll just have one talk, maybe a little bit longer, just a few minutes longer than normal, something like 25 minutes. And then we'll have some discussion. And then I think we'll also have some feedback, opportunity to give feedback on future directions of the group, kind of complementary to and in addition to the poll that I sent around about a month ago, which, some people responded to, and if you didn't, then, or even if you did, you maybe a chance just to chat with us about future directions. But we'll have the talk and the Q&A, which will occupy the main chunk of time, and then, we'll get off before an hour has passed, so we'll have a little extra time for other things compared to other days when we run a webinar to an hour and a half or more. So hopefully that will be appreciated and work well. Just quick announcements as we like to do. And as always, if you know of something or are organizing something and want it to be broadcast, let us know and we'll put it on either in an email or in the next webinar like this, or both. So the links for this stuff, if you don't know of it already, can be found at the Google Sheets tiny URL there at the bottom. So these are all compound events, related things coming up in the next few months. All right, so I will stop sharing and turn it over to Beth Tellman, who I will briefly introduce. So Beth is an assistant professor in the School of Geography, Development, and Environment at the University of Arizona. And her research considers the imprint of global environmental change on vulnerable populations, especially related to risk, flood risk and land use change in low and middle income countries. And what Mona and I, it was Mona's idea to invite her, and we thought her work was unique in kind of fusing a socioeconomic lens with remotely sensed data and considering kind of the interaction of different hazards through that. So with that, then I'll turn it over to Beth. Thanks again for speaking today.
Yeah, thanks for having me. So I'll share my screen here and share some of my work and hopefully have a good discussion about what is kind of most relevant to this group. So I'll give some sort of broader overviews, but happy to dive into any methods or kind of detailed conversations folks want to have based on what's relevant to you. So we'll be talking today about mapping floods from satellites and what that can help us do to better not just understand flood exposure and risk, but then what do we actually do about it, right? And not just thinking about how do we adapt to risk, but how do we actually change sort of the power dynamics of who even experiences risk in the first place. And sort of I've started to get involved with this mostly through my graduate students through sort of the broader climate justice movement. So I want to talk a little bit about some of that work because it's something I really want to encourage other climate scientists to actively get involved in so we can all do something about the climate crisis and make a bigger difference just beyond the science papers that we publish. I'm really passionate about that. Before I dive in, I want to give a few advertisements. So I'm on the steering committee of the Global Flood Partnership. This is a really great small meeting if you do flood work. This is in Leeds this year in September, and our theme is Floods and People. It's a really cool conference of both users of flood data as well as scientists. So it's a really great place to sort of engage with society if that's not something that's a regular part of your work. We're going to have an awesome list of keynote speakers and small workshops, so consider joining. I put the registration link here, but email me if you have more questions about it. This will be at Leeds, hosted by Mark Trigg. The second thing I wanted to advertise, I know this call is probably mostly scientists, but we have a working group on flood recovery and adaptation funded by the University of Arizona Institute for Resilience and Resilient Environments, and we're recruiting a community-based member, so not a scientist, to be a part of our group. They'll get paid for their time and paid travel and participation. So please send this around to folks you might know in your network who would want to participate and engage more with scientists and infuse a little more data in their work. Okay, enough advertisement. So thanks for the intro. Just quickly, who I am is a scientist and I'm a geographer. So what that means is that I really do both social and natural science to try to understand not just where the world is changing, but why and what we do about it. And I've mostly worked on land use change. I'll have some work on deforestation and urbanization, but today I'll mostly be focusing on my work related to flooding. And I'm really passionate about how we, I mentioned this in the beginning, address the consequences. So I've started a company as one way to make my work more useful outside academia. It's called Cloud to Street. I'll talk a little bit about it today. I work a lot with governments. So one of my NASA grants is with the Bangladesh Flood Forecasting and Warning Center. I've just started working in my regional flood control district in Pima County in Arizona. And I also am working on writing grants right now with a nonprofit group of lawyers called the Texas Rio Grande Legal Aid through one of my grad students, Lucas Belluri. And I'm really excited about the role that science and lawyers actually can play together in the climate justice movement. So I'll talk a little bit about that. Almost all of the work you'll see today is funded by NASA, but it's to fund kind of these civil society partnerships in large part to figure out how we can make flood data matter. So I'll talk first about the science of what I'm doing, and then the second half, I'll give kind of a sense of the applications of this work to hopefully generate some good discussion. I'm excited to hear about your thoughts about applications of flood satellite data too, if you have any. So the context of why satellite data can be really useful is that especially at a global scale, flood models have a huge uncertainty. It's really hard to predict where flood water might go for extreme events for a lot of reasons. Difficulty in high quality elevation data, not enough stream gauges to calibrate models. And so satellites can be really helpful in helping us understand where our model's not doing a great job. So this is zooming in to the Eastern Nile region, and you can see this flood event in blue in 1998 captured by the Landsat satellite. That's like totally different than where global flood models predict where water will go. And that's because of human adaptation. Lots of levees have been constructed over time along these rivers. And so instead of water kind of flowing out of the river as a model might predict, a lot of the water is being shunted sort of through canals and irrigation districts and flooding sort of in a totally different pattern. And so satellites can really help us to see not where we predict water will go, but where did the water actually go? Satellites are really helpful in frequent events in particular. Of course, because it's such a short record, we really only have about 20 years of record to see large-scale flood events. And for really frequent events, you can get a sense of, you know, where is there human adaptation and we haven't seen a lot of floods versus where flood models predict a lot of flooding in the 5-year return period. Like this probably isn't happening at this large scale. And conversely, there are some places, this is sort of off floodplain inundation. This is in Timbuktu, Mali, where it's predicted to be like a very rare event, 1,000 or 500-year return period that we've seen in some places flood almost every year. So these are the ways that satellites can help us make flood models better and give us new perspectives on where is water actually going on the ground. And we've got to get better at flood modeling and help use satellite data to make that better all of the time, because we know flood risk is increasing and it's increasing in really inequitable ways. So this really important paper by Ollie Wing published this year showed first that more than half of flood risk is outside the areas that are mapped by the federal government management authority in the United States. So that's a problem. And second, where floods will increase the most is disproportionately borne by Black communities in the United States. So we have real inequality in who climate change is going to impact the most, and we've got to do something about that. And the problem with inaccurate flood models is that it has all of these cascading effects on our ability to manage risk effectively. So I'll just give two examples in the US. In Hurricane Sandy in New York, 10,000 homes were flooded that were not on the FEMA flood maps. In Hurricane Harvey in Houston, there were 80,000 homes that were flooded. And this is actually a sign that appeared in someone's front yard in Houston, like being like, oh my gosh, we need insurance. We didn't have access to this federal program because we were left off of those maps. So that data leads to a real lack of financial adaptation strategies. And we've got to do better as the world warms, unfortunately. So hopefully you've sort of captured this overarching thesis by now. More satellites being launched every year means we have more opportunities all the time to observe where real floods happen and can give us a better sense of where risk, what risk is actually going on. So this is an example of what, if you haven't worked with flooding and satellite imagery, of what it actually looks like. So we're sort of going back and forth here in the multicolor image between Sentinel-2, a radar satellite that can map water through clouds, and Sentinel-1, that's the green image, that's an optical satellite. And you're seeing these sort of before and afters of the image, and a machine learning algorithm extracting out where that water is. And so that's sort of the process of mapping a flood. This training data set we actually released. It's called Sun1 Floods 11, so you can play with it yourself to train your own machine learning models if you wanted to for those two satellite sensors. So let's talk about what we actually learn when we map a lot of floods around the world. The global flood database that we released in August in Nature got a lot of media attention, showed that up to 86 million people moved into a floodplain that we observed flood in the last 20 years by satellite. So this is like new construction in places we saw flood. And we saw this all around the world, mostly concentrated in Southeast Asia, where we had the most highest success of mapping flood events. We only mapped 900 floods, but within that region, we saw a lot of change all around the world. We used the MODIS sensor at 250 meter spatial resolution and a cloud computing remote sensing platform called Google Earth Engine to build this database. Most of the flood events, as you can see, are caused by heavy rain, but a couple other causes like dams, snowmelt, or ice. And this is coming from the Dartmouth Flood Observatory database, if you've worked with that data before. So we worked with them to basically make a consistent flood map for every record of observation that they had. And when we started zooming in around the world to different cities, we found that there were some places like New Orleans where we saw population decrease. This is actually the flood footprint of Hurricane Katrina. Lots of people moved out in that zone between 2000 and 2015. But other places like Dhaka or Guwahati, India, that we're seeing rapidly urbanize and communities infilling in places where flood waters had previously been. This is a really concerning trend. We saw the most exposure and sort of changes in population actually right below dams and levees that ended up later breaking. And this is what hydrologists often call the levee effect. So we adapt, we build a dam or a levee, land prices increase, people feel safe, they move into that area, but if it ever breaks, which we're at huge risk of for thousands and thousands of dams actually in the US right now that haven't been properly upkept, that water can affect a lot of people. And so those are the places actually where we saw some of the highest increases in population exposure from floods because of the levee effect, we think, in these dam break areas. Kosi, India was the place where we saw kind of the largest affected numbers of this. And all in all, when we compare this sort of change in flood exposure to what a flood model had previously predicted in another paper, we found that we were getting rates like 8 times higher than what models were predicting. And so really these satellite observations were giving us sort of a new insight into where this was happening around the world. Countries in red are where we saw the highest increases in growth in population in floodplains relative to the population growth rate of that country. Places in green or blue is actually where we see somewhat of a decrease compared to the total overall growth rate of that country from 2000 to 2015. All of this data is publicly released. We made it like a GUI platform so you can interact with it. It's an asset in Earth Engine. All the code is open on GitHub, so you can download this data as TIFF files or interact with the whole database for your own purposes if you're interested in flooding. But the MODIS sensor is way too coarse to resolve flooding in urban areas because of the size of the pixel. So this is the flooding in San Pedro Sula, Honduras, and Hurricane Eta and Iota. And you really have to get down to these commercial 3-meter resolutions to make out, you can see here in brown and then in false color in green, sort of the flooding that happens along side streets and between homes. So my lab now is working on figuring out how to use machine learning to make better flood maps from commercial data and also fuse multiple sensors together to get a sense of what the urban flood footprint actually looks like. I don't have time to explain convolutional neural networks, but the basic way that they work is by extracting features from simple to more and more complex to detect flood objects in imagery. So this is like learning patterns beyond what's happening at that pixel to separate what flooding might look like in a desert versus a more tropical area versus over here in an agricultural field. And they're way, way better. So CNNs or convolutional neural nets are far outbeating traditional algorithms that we had previously to map floods by quite a lot. This is just measuring one common metric intersection over union to do this that my grad student worked on. The other challenging thing is that floodwater moves fast in urban areas, and it's not like we have, a satellite passing every 10 minutes. So you've got to use all the satellite observations you can with public data. These dots here represent an observation to try to get as close as you can to the peak of the event. So here you see this is the precipitation from that flood event. Max flooding probably occurred somewhere in this range, but we sort of have spotty satellite coverage. So you've got to combine the satellites, and we're now working on trying to fuse observations together with coarser spatial data that has a more frequent overpass to fill in these gaps. So no results from that yet, but it's a work we have in progress. But what really is underlying and enabling these different machine learning methods is labeling lots of data. So you have to have many, many examples for the model to see what is water versus what is not water. And so over the past year at my lab, we've been building a massive kind of library of training data that we'll be releasing maybe by the end of this winter, but probably early next year, all around the world. We've got urban flood events, we have rural and agricultural events. We're labeling it with higher resolution PlanetScope data, coincident with many other sensors. We're also testing a new commercial sensor that's sub-meter resolution called Black Sky. So we'll be releasing a lot of this data that hopefully will be useful to other scientists training machine learning models or who just want better information on floods. Okay, so that's some of the science. I'm going to talk about applications, and then we'll open it up for discussion. So the first application I want to talk about is work that my company, Cloud to Street, has been doing. I co-founded this company about 8 years ago with Bessie Schwartz, who's the CEO, and we now have about 20 employees who have built this really incredible platform for monitoring floods in near real time. And we do this in an operational capacity for governments and insurance companies. This is sort of like the level of reliability that it's really hard to build in academia, and I found it much easier to sort of, and more appropriate, to be honest, to do this in a commercial space. We've worked in nearly 30 countries around the world, supporting humanitarian aid and relief efforts, and also underlying new types of insurance. And the way the product works is that we ingest as many satellites as we can in near real time, automated in the cloud, run impact numbers on who is affected, what roads are blocked, etc. And then we have these automated reports that we make together with our clients, depending on how they want the information. And sometimes they upload their own observations into the platform too. So I'm going to tell just one story about where this data was used. This was a couple of years ago, but I like to tell this story also because it's published, and so you can check out this book chapter if you want to sort of read it more in detail. And the World Food Program was dealing with a situation where there were 4 refugee camps that had moved over from the Democratic Republic of Congo into the Republic of Congo on the other side of the river, and they wanted to know, are any of these 4 refugee camps at risk of flooding, and should they be moved? So we mapped historical inundation through a variety of satellites, and we did find that there was one of the 4 camps where we had seen it flood 3 times. We recommended relocating that camp. They were glad that they did, because the following year, that region had a massive flood. And there were up to 7,000 people more that could have been affected had that relocation not been recommended. In that following year, the World Food Program in Republic of Congo was able to secure $11.5 million in emergency funding based on the data that we provided. It's really, really important to have good data to get more access to humanitarian aid, because you're more likely to get more money if you have the data and evidence to show it. And we also enabled cash transfers to nearly 150,000 households, because we could pinpoint exactly which farmers had most been affected by crops over time. So this is just a really basic story of how flood monitoring and historical flood risk data can really make a difference in decision making and pinpointing exactly who gets access to aid and who needs it. So Cloud Street is continuing to do that work all around the world. You can check out our website. We're hiring right now as well, so if you know product managers, please send them our way. I want to tell another story about use of satellite data in the humanitarian sector, and this is for insurance. This is work that I started during my postdoc in Colombia. And the idea here is that if you don't have financial protection from floods, then you can't invest in your livelihood. If you lose your crop, your entire crop, you may have to sell off livestock or take your kids out of school, and that's going to threaten the sustainable development of your family. But if you've got insurance capital, you don't have to make those tough choices. So satellites are being used in order to provide new types of insurance that have never been able to exist before in countries like Bangladesh that has less than 1% of insurance uptake. And the way that it works is there's a pre-identified threshold, and I'll explain sort of how we estimate those thresholds. And then when the satellite estimates how much inundation there is, farmers can get an automatic payout. So Green Delta Insurance Company kind of did the sort of first satellite-based agricultural flood index insurance in the world with farmers in Bangladesh. The way that these contracts are written is that you get sort of, in this example, fractional inundated area of a region, a district, or a village, or any arbitrary unit, and estimate the return period of that region and what that sort of financial loss is equivalent to. And so you can write a contract that triggers at a specific amount of inundation and will pay out a specific amount. But you've got to be able to estimate the return period of that inundated area, which is tough when you only have a 20-year satellite record. And we're talking about events here that are extreme by definition. So you've got to figure out the difference between, it's somewhere like Bangladesh, where 30% of the country may flood on any given year in a way that's not harmful. Where is the threshold at which you start to have so much flooding that it's causing a harmful flood event? And that's what you've got to figure out when writing an insurance contract. So an example of how this works is, say the country of Bangladesh, sometimes governments actually buy insurance for their own budgets, estimate that when 40% or more of the country is flooded, they want to receive a payout to cover $200 million in losses. So we have a record, we can estimate the expected frequency of that event and price an insurance premium. Well, what's hard is that the best satellites to do that, like a radar satellite, Sentinel-1 that can map floods through clouds, way more correlated with damage than these optical satellites that are cloudy, like MODIS, sometimes so cloudy that you don't even get correlations at all with damage from the event. The good satellites have a really short time series. And so it's hard to estimate a return period and trigger on the same sensor. So you've got to figure out a solution. And my lab has been working on data fusion to try to work on this problem. So what we've been doing is training the MODIS sensor that has this 20-year record to try to reproduce the signal that looks a little bit more like the Sentinel-1 sensor, so that we can estimate return periods on MODIS, but trigger on Sentinel-1, kind of the better sensor. So that's what we've started doing recently. And so initial experiments were just training a random forest algorithm on fractional flooded area that we upscale to 500-meter resolution, throw in an elevation DEM, all the MODIS bands, and a couple of different other features. And we're getting like okay results. So the blue line here is the observation and the red is the prediction. So we do get a good sense of sort of capturing the flood season, but we're still underestimating at the peaks, mostly because of cloud cover. So we're going to have to go from random forest, we think, to probably deep learning that incorporates a lot more spatial and temporal information to try to fill in some of those cloud gaps and boost these R-squareds a little bit, because we're not happy with it yet. But if we take that model, we can then make this 20-year time series that sort of acts like Sentinel-1. And we're finding pretty good correlation between our fusion data set, this line in blue, and a flood model estimate from the government that at least gives us a sense, yes, we're capturing the peak years. We think this is probably going to be useful for estimating return periods. I'm going to keep moving, but I showed a link to the paper where we talk about this more because I want to get to discussion and show you at least these two other interesting examples about climate justice. So that's sort of the work we're doing to support flood index insurance and fusing satellites. Okay, so I'm hoping this is obvious to folks that live in the United States, but it is a truth that bears worth repeating, and I've found this empirically, and we keep seeing more and more publications validating this truth, that relative flood damage is higher in specific places in the United States, Hispanic, Black, and Native American communities that have received historic underinvestment in flood mitigation because of structural racism and blue lining. I won't go into all the mechanisms here, but there's a lot of evidence to support that we don't have as much, we have not built flood mitigation infrastructure well by design in these communities, and they flood more and they lose more from a flood. So that's a problem that needs to be addressed. But it's not just that flood exposure is unequal. The actual access to who gets data about floods is unequal too. So for example, Hurricane Harvey in Houston, people were buying homes in subdivisions that had a lot of flood risk and they didn't know. And there's some really interesting investigative journalism that uncovered basically that sometimes developers were paying off people in government to intentionally withhold that information to not decrease home values in that area. So we've got to think about who produces flood data and who has access to it and doesn't. The financial sector is buying all sorts of commercial flood data that the US government isn't using. And what that means is that banks are able to offload mortgages that are at climate risk. This could cause a huge problem in housing markets and another housing crisis. And this is also something investigative journalists and Jesse Keenan have been writing about. So this is a problem. And what we need to do then, I think, as for me at least, as a satellite-based flood scientist, is think about how do we make sure that this data is for climate justice and not against it. So we have to think about who are we working with and how to make sure that we use this data to ensure resources are redistributed to communities who have been disproportionately harmed or inadequately supported. So for example, the Biden administration's program Justice 40 to try to get more money into these communities? How do we use data to and work with nonprofits and community organizations to make sure that happens? My grad student was Hannah Friedrich, was just at the Gulf Gathering for Climate Justice and Joy, trying to figure out who's working on different parts of the Green New Deal and how do we as climate scientists engage with that work. I'll give kind of 2 examples that my grad students are doing, and I just find what they're doing so important and inspiring. So Lucas Belluri works on flood injustice in the Rio Grande Valley. And this is a region along the US-Mexico border where there's a lot of informal settlement, often referred to as colonias, that have had repeated flooding and environmental racism, out of date, inadequate FEMA maps. FEMA actually got sued by nonprofits because of discriminatory practices and who is even able to access FEMA data. And Lucas has been writing about this work. Texas Rio Grande Legal Aid and a community organization called Lupe had a successful lawsuit after Hurricane Dolly to try and get money to folks and change these practices. And there's also, because when there isn't adequate federal aid, loan sharks come in. And there are predatory loans that people take on to try to repair their homes. And so we've got to think about how we can change this situation and redistribute who gets access to what aid. So we just wrote a NASA grant with the Texas Rio Grande Legal Authority, and we're writing another Google grant. We'll turn it in a couple of weeks to try to use satellite-based flood data to fill in gaps in outdated FEMA maps and current information to help them build more lawsuits like that, maybe get more money from federal programs, and sort of change the situation and give them data to sort of supercharge the work that they're already doing. The second example I want to talk about, my grad student Hannah Friedrich is working on, is thinking about how do we not just map where the water is, but how do we measure rates of recovery from satellite to understand the inequities in that program. So this has been well documented in research and different case studies, and Hannah's figuring out how do we do this on a large scale using satellite data. So what she figured out, and will be continuing through the NASA Finest Award she just received, was that you can actually map roof damage and tarps on roofs when they go on and when they go off after a disaster as an indicator of damage and recovery from satellite-based sensors. And she's then combining that with data on federal assistance and census data to better understand, do people really recover better when they're getting federal aid, and who's not getting federal aid, and what is the lag time that that's causing in their own recovery, and how do we understand that on a really large scale. So I'm really excited for sort of the next phase of her work and the organization she's working with on the Gulf Coast to think about how to use this data for advocacy, better buyouts, and better programs on federal assistance. So I sort of wanted to end here and leave folks with this. Again, we know this, we've been seeing this in the news. This has been an experience that civil society movements have been telling us about for a long time in the US. And how are we as climate scientists going to engage in this reality and change this situation? We can't just do better climate science and publish papers. We have to think about how does our work engage with climate justice and environmental racism to change these dynamics. I think that's really important. And satellite-based flood maps have one small role to play in that bigger picture. So just kind of a summary of my talk today. We can use satellites to spotlight regions where floodplains have been growing in development and populations are at risk. We can use historical records to try and relocate communities where places get repeat flooding again and again. We can see floods in near real time and make sure people are getting the aid that they need. And we can also use this data to come up with new types of financial mechanisms like index-based insurance in places where it has never existed before. But also, these maps could be used by only bankers or developers to make more money if we don't think about how we're increasing access to data and working with nonprofits and lawyers to make sure they're getting that data too, to demand more justice in our system. So I know this is really cliche to say, but if you're a scientist and you want to support climate justice, you got to get more engaged outside of academia and civil society. And again, you can come to the Global Flood Partnership and we can help you make some of those connections to do that relevant work that our world so badly needs. And second time I'll show this ad, if you know someone working in a nonprofit or community who wants to get more involved with scientists, please send them my way. Thanks to NASA for supporting this work and all of the students who have been doing this incredible work. And I'll end there and excited to have some discussion with y'all. Sharing.
Yeah, thanks so much, Beth. That was very inspiring. You have a lot of energy, obviously, and you're applying it to very meaningful projects, and the open data, and the conversations about resilience. It's really great stuff. I will stop.